Hi everyone, welcome to this channel, the Merchant Construct-preneurs and Tutors. Yeah, this is another topic to discuss everything about construction engineering, structural engineering. So today we'll be looking at a very important topic, which is how to calculate the reinforcement density for column, beam, and slabs. So this is is a way of preparing the reinforcement quantities or volumes even while your reinforcement schedule is not out, like your bending schedule is not out, you're not done with your design. So I'm going to explain this bit by bit. So first let us look at what is reinforcement density. Now reinforcement density is standard steel intensity per cubic meter of in situ concrete, in which is used to convert structural volumes into tangible, billable and manageable steel quantities. So what this saying is, you want to know the quantity of steel or the density of steel that is inside a gross quantity of the concrete, right? So it's total mass divided by the total volume of concrete, and that's the reinforcement density of of that particular section. So now we are going to look at this thing now. The reinforcement density answers the fundamental question for the quantity surveyor: how much steel is embedded per cubic meter of concrete. So if I have a concrete of this dimension, like a beam of 0.3 by 0.6 by 6 meters, so the concrete volume is actually multiplying this length times breadth times height, but then the detailed bending schedule is showing that it is having 147.9 kilograms. So what you have to do is divide the total weight by the volume of concrete. So when you divide it, you have 137 kilogram per meter cube. That's the reinforcement density. That is how much steel is embedded in this. So we want to know, if you want now, the consequence surveyor now wants to know individual number of steel. Now that then you now go on with his own calculation. So this idea actually gives the structure and the quantity surveyor an idea of what is embedded and how we should go about it. So I think the examples we are going to go through will explain further, right? So this question, like given a beam 6 meter long, 0.3 and 0.6 deep, with the reinforcement details shown below, you should calculate the reinforcement density just as the image seen here. So we are going to take 1 meter strip. Once you're able to get a strip, then irrespective of the length of any beam, is easier. Instead of doing for each beam with its own peculiar dimension, so we take 1 meter strip, and the reinforcement we have 220 at the top, 40 to 25 at the bottom, and the length is 10 mm at 200 spacing. So first thing first, we are going to compute the volume of concrete. There is a meter cube per meter length. You are using a strip. So the volume will now be length times width times depth, and then we have this as 0.18 meter cube per meter, right? Always remember it is per meter because we are taking a strip. So the next thing is to compute the weight of the reinforcement, and then the weight of the rebar is number of rebars multiplied by weight per meter of the specific size. This weight per meter is something that can be calculated and you can get it online. So for each reinforcement have their weight per meter. So once we know the weight per meter of this and the number of reinforcement, we are good to go. So the weight here will now be 2 multiplied by 2.47 because we have 2 T20 at the top. So we'll be having 4.94 kilogram per meter. That per meter is not a mistake. It's still because we are considering a strip. Assuming we are taking the actual dimension, it will be kilogram, right? So for the bottom bars, so we are doing the same thing. We have 40.25 at the bottom, and then the weight per meter of 25 mm rebar is 3.85. So once we multiply 4 by 3.85, we have 15.40 kilogram per meter. I hope that is clear. So for the length, we have 10 mm at 200 mm spacing. So the weight per meter of a 10 mm bar is 0.617 kilogram per meter, right? So the link length, we need to know the link length. So you check the beam perimeter minus cover minus the hook. So we're having it as 1800 millimeter. Then so the number of links now we have the span or length divided by spacing. So when we divide that 1 meter, because that's the strip we are taking, divided by 200, you have five numbers. So weight will now be number 5 times 0.1617, that is the weight per meter of it, times 1.8. So we have that 5.553. So the total weight of rebars in this beam section is weight of top plus weight of bottom plus weight of links. When you add them up together, you have 25.893 kilogram per meter. Then the last thing is to find the reinforcement density in per meter length. So total weight divided by total volume, just have to calculate the total weight 25.893 divided by 0.18. So we have 144 kilogram per meter cube per meter length. Then for 6 meters that was in the question, you have to just multiply 6 by the reinforcement density that was calculated, and we have it as 864 kilogram per meter cube. This is for the beam. I think it's straightforward. You get first the volume of concrete, get the weight of each reinforcement, and then find the reinforcement density. As easy as that. So let's look at the next example, that's for column. It's also the same thing, but we are taking the strip along the height, that's the length of the beam. So we have 4 meter high column, 0.4 wide, and the breadth of 0.4. Reinforcement details are shown in the question, in the image, right? So this is the section. We have 40, 16, and a length of 10 mm. So we are going to do the same thing, considering 1 meter strip of it. Once we're able to get 1 meter, irrespective of the length of the column, we are good to go. So if you get a unit value of any calculation, you are good to go. If it's volume of concrete that you need per cubic meter, once you get that, you should be able to, if you now have 100 cubic meter, just multiply that value you've gotten for your 1 cubic meter, and then you get your value, right? So now let's go into the solution. First thing, as usual, we compute the volume of concrete meter cube per meter, right? So the same thing, width times breadth times height. We have it as 0.16 cubic meter per meter. Now we want to compute the weight of the reinforcement. Weight of reinforcement is still number of bars times weight per meter of specific rebar size. So for the longitudinal bars, we have 4016, and then the weight per meter of 16 bar is 1.58 kilogram per meter. So the weight of the longitudinal bars now be 4 multiplied by 1.58, we have it as 6.32 kilogram per meter, right? So we are considering 1 meter strip. That is the reason why we have this. So we move to the next one. So we have the length also. So for the length, we have 10 mm at 200 mm spacing. Also, the weight per meter of 10 mm rebar is 0.617 kilogram per meter. Then we need to find the link length, just as we did the beam perimeter minus the cover on all 4 sides plus the closure of the link. We have it as 1580 millimeter. Then number of link, we are considering 1 meter strip. So 1 meter strip, 1 meter divided by 200 spacing, we have 5 numbers. So total weight will now be 5 multiplied by the weight per meter of the link size times the link length. So we're able to get that for the link as 4.87 kilogram per meter. I hope this is clear. For the link, especially for the link aspect of it, we need to get the length of the link after getting your number of rebars and getting your the weight per meter of the reinforcement. So total weight will now be weight of longitudinal rebars plus weight of links. When you add them up together, you have 11.19 kilogram per meter. Then lastly, we have to do the calculation for the reinforcement density in kilogram per meter cube per meter length. So total weight divided by total volume. So once you do that, you have 62 kilogram per meter length. Then for a 4 meter height of column, because that's what was in the question, so multiply 4 by 62, we should have a total of 248 kilogram per meter cube. That means 248 kilogram of reinforcement is embedded in that 4 meter height of column with that dimension, right? So this is information that the QS will now make use of in going around the zone calculations in estimating and planning. So lastly, we look at how to calculate for a slab. So you're given a slab 0.2 meter thick, 3 meter wide, 5 meter long. So you want to calculate the reinforcement density required. And this we have the both main and distribution as T12 at 200 millimeter spacing center to center, and this is the dimension of the slab. So we are taking a square meter, right? So that's 1 meter by 1 meter, instead of taking the full dimension as 5 meter by 3 meter. Once we get a square meter, we are able to multiply this and get, irrespective of the area required for the slab, we're able to get that, just get per unit. Right, so we'll go straight into the calculation, right? So the first thing, as usual, we used to do, we compute the volume of concrete. So this time should now be in meter cube per meter square, because we're taking a unit square meter. So volume will now be width times breadth times height. So the height is the 0.2, width and breadth is 1 So we have 0.2 cubic meter per square meter. The next thing is to do is to compute the weight of the reinforcement in kilogram. As usual, it is given as number of bars times weight per meter of specific rebar size. For the distribution rebars, we are using 12 at 200 spacing. So number of rebar will now be span, that is the LX, divided by spacing is still 1 meter. 1 meter divided by 200, we have 5 numbers, right? The weight of distribution bar will be 5 numbers multiplied by weight per meter of 12 multiplied by 1 times 2 sides. This one is the the length. We are considering 1 meter length. So we have 8.89 kilogram per meter per unit square meter. For the main reinforcement, we are doing the same thing. 12 rebar at 200 is required. So number of rebars will now be span divided by spacing. It is still 1 meter. So 1 meter divided by 200 spacing will give you 5 numbers of the for the main reinforcement. So the weight of the main reinforcement will now be the 5 numbers multiplied by weight per meter multiplied by 1, which is the span, then 2 sides. Since the slab, we are considering it as doubly reinforced slab. So we have 8.89 kilogram per square meter, right? So we'll be looking at the next calculation, which is the total weight, and that is the weight of main reinforcement plus weight of distribution rebars. When you add both of them together, you have 17.78 kilogram per square meter. Then the last thing to do is to, as usual, reinforcement density. Total weight divided by total volume, you have 17.78 divided by 0.2. So we're having that 88.9. Then the slab that was given to us initially was 5 by 3. So that is 15 square meter. So for a 15 square meter, will now be 15 multiplied by 88.9. That is, we have a 1,333.5 kilogram per cubic meter. Right. This calculation is very, very important to the QS, because without that, a planning cannot go on. You cannot be waiting for the structural drawings to be ready before they can go ahead with the planning. So this gives an overall idea of the reinforcement that is required. So a little of addition for wastage, for lapping will be done by the quantity surveyors, and then work can go on while the main structural drawings are being prepared. And if the structural drawings are, the bending schedule is ready, then we are good to go. There's nothing to